Hello, everybody. We have one more fundamental differential equations result that we want to prove. And that result is known as continuity with respect to initial conditions. So we want to know that given some differential equation, that the solutions evolve in a continuous fashion. So on here, I have started off up at the top with a reminder of what the definition of continuity is. And then I'm going to draw a picture and show you what we're trying to, what that implies about flows to differential equations. So it says a function f is continuous if for every epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and y is less than delta, then the distance between f of x and f of y is less than epsilon. You are used to seeing this with absolute values instead of distances here and here, but I just wrote it with distances since we just introduced that concept. And the reminder that an absolute value function, absolute value of x minus y, is a distance function on R. So this is just a slightly more general statement of the definition of continuity. So what does that mean in this context? Well, suppose I'll draw a picture. So I have some point, some initial condition here that I'm going to call x sub 0, and it goes somewhere in time t. So right here is phi of t x 0, and we want to think about that t as being fixed. I then want to, so the definition of continuity says, given any epsilon or for all epsilon. So that puts a small circle around centered there. So that circle is centered at that result. The radius of this circle is our epsilon. That was not good. Try that again. That radius is epsilon. And what I would like to be able to know is that if you give me that endpoint right here and that epsilon distance right here, can I find some other circle around here such that things inside of it end up in that exact same circle when I flow for that exact same amount of time? So let's pick some different color down here, maybe green. And I'm going to come here. I think it might be easier. So we get some other circle centered there. And this radius of this circle is now delta. And what the continuity theorem says is that if I take any point in here, some other initial condition, then it is going to end up back there. And that other initial condition is y sub 0. All right, so that's what we want. So that delta, that disk, doesn't have to be the same. You know, there's no way it's going to be the same radius as the other one, except in really special situations. So that's the picture that you should have. The statement of the continuity, well, this doesn't look like that, but this really is the continuity theorem right here. This is continuity, and I'll explain why once we've read the theorem. It says, given some differential equation, x dot equals f of x. So I'm doing this just for autonomous differential equations, but we could do the same thing for non-autonomous ones. And again, the function f and the derivative should be continuous. It says, all right, so here's the heart of it. It says let phi of t and x 0 and phi of t y0 be solutions defined on some interval of time, that's t0 to t1. Then there exists a k greater than 0 such that for all t in that interval, the distance, make that go away, how do we do that? The distance between phi of t x0 and phi of t y0, so the distance at the end is less than or equal to the distance between the initial conditions times e to the k times t minus t0, so the time of flow. So this really says that, so this actually is a more detailed theorem than just saying it's continuous, that says that solutions, they may grow apart from each other, but they do it no faster than exponential. So this actually gives a limit on the, so it says solutions can separate no faster than exponentially. And so how does this up here give us continuity? Well, I think I'm going to try to clean up just a little bit here. I'm going to erase my picture, give myself just a bit more room. And then, so what we want, right? The continuity says we want some bound on epsilon. Or the distance between f of x and f of y. In this case, instead of f of x and f of y, those are phi of t of sub x naught, the solution that starts at x naught, and phi of t of y naught, the solution that starts at y naught. So I really want this right here to be less than epsilon. So we want phi of t x naught minus phi of t y naught. I want that to be less than epsilon, the thing that's fixed. Well, that will be true if we believe this theorem. That is true if the distance between phi of t naught x naught minus phi of t naught, remember, is the starting value, comma, y naught, times e to the k times t minus t naught, if that is less than epsilon. Right? So, but what is this stuff right here? This is the distance between, the starting values. So this is like the distance between x and y in our definition of continuity. So if I want this to be less than epsilon, we can choose this, which is like our delta, to be less than or equal to epsilon times e to the minus k times t minus t naught. So if I choose the points so that initially they are closer than that they're within that delta ball, so their distance between x naught and y naught, or the starting values, is less than epsilon times e to the minus this, then since after time t, the distance between them is that times e to the positive k times t minus t naught, those things would cancel each other out, and you would get that phi of t minus t naught, phi of t x naught minus phi of t y naught is less than epsilon, right? So, so this would be, so see if I can try to write this on here, the very bottom. Phi of t y naught, that distance is less than epsilon e to the minus k times t minus t naught times e to the positive k t minus t naught from the theorem, and those things cancel out, and so we get epsilon. So this theorem will prove, or is a broader theorem than continuity, but it implies continuity by that argument there. All right, so I'm going to stop this video, start another one, and we're going to proceed with the proof of this theorem.